time to take all of these sinusoidal functions and apply them to something that is kind of a little bit more meaningful to us. For example, look at a sinusoidal function. A sinusoidal function has a periodicity, which means it's a repeating pattern over a period of time. Think about it. Sunsets goes sunset, sundown, sunset, sundown, sunset, sundown. Look at that. Sunrises, same thing. Seasonal temperature changes. Oh, so guess what? The temperature, average temperature is warmer in the summer and then it gets colder in the winter. Oh my goodness, there's another sine function. Look at tides. High tide and low tide. And the very next day does the same thing, which is kind of cool. Music, tone. Do you realize that music is a sound frequency and the sound frequency goes up and down like this? Oh my goodness. But what happens when you amplify the sound? Check this out. You're amplifying the same sound. You're just changing the amplitude. You're not changing the frequency, because if you change the frequency, guess what you're doing? You're changing the tone. Aha. So what could be a high-pitched voice because you're changing the frequency could be a low. Oh boy, that sounds like auto-tune to me, but anyways, and that's how it works. Same with comet appearances. So the comet shows up and then it disappears and then it comes back and so on and so forth. How do you think they figured out when comets return, like Halley's Comet? It's all based on a sinusoidal function. Oh, is there any other important stuff we need to know? Yes. Okay. Most of the equations that you're going to write, instead of using an x, you're going to use time, t. Okay? The period then of this graph will, of course, then be in some sort of time units, whether they're seconds, days, hours, years, whatever. Okay? Right? Now, you'll also find a pi in these particular things. Reason why is because think, if you've got a period here, right, and you're going to divide it by a simple number like this, like the b value, of course, you're going to end up with some sort of, yeah, guess what? You're going to have some sort of function of pi in your equation. So that means the stretch factor here, the horizontal stretch factor, will always, always, always be in terms of radians. Okay? You'll never do this in degrees. Every single time it has to be in radians. Okay? So flip your calculator over to radians right now, baby, because you'll need to. So, for example, you know how to figure this out. We've done this 1,000 times. If I tell you it's a period of 5, then the b value becomes, yeah, of course, there's the b value, just put it over 5, 2 pi over 5. If the period is 10, guess what? Put a 10 in here, and look at this. You can reduce this from 2 pi over 10, yeah, down to pi over 5. You can reduce it if you want to, okay? Really nice. So what does the general equation look like? Tell me if this looks familiar. Of course. 100% it's familiar, because this, in fact, is the basis of all sinusoidal functions. But the important thing is, remember, this has to be in radians, okay? It has to be in radians, okay? So, in some cases, a sinusoidal function will be given in the question, and others, yep, we're going to have to derive it. That's where the fun starts, deriving where this equation comes from. So, let's not procrastinate no more. Let's go. So if you look at this particular question, I've given it to you. I've given you the actual function. So I don't like the way this is written right off the bat. So I'm going to write this as d as a function of t. Notice I haven't even read the question yet. 5 cos 0.5 t plus 12. Oh, how incredibly beautiful. Now that looks like something I'm familiar with. Okay, now let's read the question. It says, this is the depth, D, oh, okay, of water in a harbor, right? Oh, so obviously you're dealing with tides, right? High tide and low tide, where T is the hours, oh, look, for a day. Oh, okay, I can do that. It says, determine the maximum and minimum depths of the water. Well, you know and I know that you're smart. You know and I know that you can take this amplitude here, because that's our amplitude of 5. You can say, oh, there's our average depth of 12, right, because it's right in the middle, I can find high tide by adding the 5 to this and then subtracting the 5 from this. I can find my maximums and minimums because if you think about it, there's the function, right? Right? There's the d value, which of course is 12. There's the amplitude of adding 5 to it and subtracting 5 to it. So 12 plus 5 means that my max is going to be at 19, or sorry, at 17. And our min, of course, 12 minus 5, you know that this is going to be at 7 meters. So you can figure that out just by looking at this particular equation. This equation gives us a lot of information. Then it says determine the period of this function. Okay, well, hey, look, check it out. There's our b value. You know that period works out to be equal to 2 pi over the b value. So 2 pi over 0.5, work that out, you'll end up getting a period then of 4 pi. Oh, easy peasy. 4 pi it is. Perfect. There's our period of our function. What does that period mean? Well, 4 times pi, if you think about it, this is 4 times 3.14. If you do that on your calculator then, 4 times 3.14 works out to be 12.56. Now, if you think about that, 12.56, what does this mean? What does this mean? For a complete high tide and low tide, you're going to need 12.56 hours. There you go. That's how it works. That's what the period means. Okay, write a suitable window setting, which can be used to display this graph of this function. Well, think about it. Okay, you got a max of 17, you got a min of 7. So think about this. Are you going to put the 0 right here? Of course not. If anything, the 0 is going to be way down here. Your d value, in fact, is going to be 12. You're going to have your maximum up here at 17. You're going to have your minimum down here at 7. That makes a lot more sense to me. That makes an awful lot more sense to me. Okay, so you know that this thing's going to cycle this way. What else are you going to do? You're going to put down your domain restriction up to 24 hours. See how that works? Very simple. Okay, now I'm going to throw this on my graphing calculator. Knowing that I have what I have, I'm going to put it on my graphing calculator right now. First things first, I'm going to notice it's in degrees. Got to get that degrees out of there. It's got to be in radians like I told you before. So mode. Flip this down to radians. There it is. Boom. Okay. Second quit. Go back to my y equals 2. Now put the equation in. Remember what the equation was? It was 5 cos 0.5 x. Got to put the x in there, even though you know and I know that's got to be a function of t. Okay. 0.5 x. And then that's going to be plus 12. Okay. Let's put our window settings in as we predicted. All right, yeah, we still started from 0 out here, okay, but we're going to go to 24 hours. Okay, 0 to 24, 0 to 24. Perfect. Next thing we're going to go, so let's go up by hours. 1, okay. Our y min, remember we had over here, minimum value looks like 7, our max was 17. Let's put it exactly as we see it. Minimum value was 7, our max was 17. Looks great. Okay, y equals 2. It's there. Punch it. Look at that. There's our beautiful graph. Oh, I can't love that anymore. Gosh, that's gorgeous. Okay, now, here we go. Ready? Boom. Now, what is the depth of the water? Now they can ask you a whole bunch of questions. What is the depth of the water to the nearest meter at 2 o'clock in the morning? Well, why even waste your time figuring this out algebraically? You just spent a whole bunch of time putting into your graphing calculator, find me 2 o'clock in the morning. But be careful. Being that this is 24 hours, you're on a 24-hour clock. So where is 2 a.m.? 2 a.m. is here. Where's 2 p.m.? That's what I'm kind of curious. Where's 2 p.m.? 2 p.m. would be, well, there's 12 noon, there'd be 1, there'd be 2 p.m., which is actually at 1400 hours on your 24-hour clock. Aha, so be careful because they're going to get you on that. So we're looking for 2 a.m., which is right here. So how do we find that? Well, isn't that a value? Isn't that a value? Don't you want to find out what is your value at 2 o'clock? So your depth at a time of 2 o'clock. Wonder what that's going to be. Well, simple. Let's go back to our calculator. Do you remember how to figure out value? Sure. Second calc value. Your value at time, remember time is x at 2 o'clock. Punch it. Look, it even gives you a little blippy there. It tells you that your depth is at 14.7 meters. Okay. Boy, that was easy. No crazy calculations involved at all. But if you wanted to do the calculations, all you'd have to do is put a value of 2 in here, right? And then throw it on your calculator, right? So if we do that, check this out. I'm going to put it on a calculator. I want to prove it to you that we're going to get the exact same number of 14.7. Okay, watch. Remember the formula was 5 cos 0.5. Now, don't forget our x here, which was here, is no longer x. We're going to change that to times it by 2 because we want it at 2 o'clock, right? Then we're going to add 12 to that, right? Because that's what our formula says. All right, punch it. You'll see it give you the exact same number, 14.7. Yay! So whether you do this using the feature on the calculator or just straight out calculating it, it gives you the same answer, no problem. But look at this question now. Look at this question now. And this becomes really kind of interesting. This question says, a ship which requires a minimum of 8.5 meters of water is in the harbor at midnight. Okay, let's get rid of some of this so I can actually read the rest of this question. It's there at midnight. Lovely. My question is, by what time to the nearest minute must that ship leave? Because you know and I know that this thing cycles between 17 meters of water depth and 7 meters of water depth. You don't have enough water. This guy's going to ground out. So he's got to get out of the harbor and he's got to be out at sea at a certain time. My question is, at what time does he have to make sure he's out of the harbor? Well, how do you do that? Well, isn't 8.5 meters a depth? It's a depth at a certain time, isn't it? So guess what? That 8.5 meters, well, wait, where is 8.5 meters according to our little sketch? Should be right around here. Well, if we do that, go back into your calculator and look at the graph again. Find me a depth at 8.5 meters. How do we do that? Y equals to 8.5. Boom. Graph it. Look at that. Its depth right now, it better be gone by this time. Because if it's not, it's going to ground out. It's below where it's supposed to be. This is your 8.5 meters. Right here, this line right here tells you it's 8.5. If you go below this line, you're going to, your boat's going to be in a lot of trouble, right? Okay, so how do we figure out that point? Of course we figure that point out just because it's an intersection, right? So second calc, find me the intersection. 5. Okay, first curve. Let's bring it right down. There it is. There's my first curve. Enter, enter, and enter. This is at a time now. There's our depth of 8.5. It better be gone by this time, 4.69. So what does that mean, 4.69? Okay, let's go back to our calculator here, which is this guy. Clear this out of here. Hit my x equals 2. There's my 4.69. So 4.69, isn't that at 4 o'clock in the morning? That's 4 a.m. But wait a second. It said to the nearest minute. So I got this 0.69 here. Guess what? That's 0.69 of an hour that we have to now convert into minutes. So how do I do that? Well, first thing I would do is get rid of that 4 because I know it's 4 o'clock in the morning. So I'm now just left with this section here, which is going to be converted into minutes, right? Okay, how do I convert that into minutes? Simple, multiply by 60 because there's 60 minutes in an hour. So you're looking at, well, he better be gone. That's 41.5 minutes. He better be gone by 4:42 at the latest. If he's not gone by 4:42, that ship's going to ground out. Yep. So they send that ship out into the sea where there's a lot of depth out there. And then the next question, if you think about it, it says, when can this guy return to the harbor? Well, think about it. Let's look at the graph. Look at the graph. Okay? Let me clear this all out of here and you'll see it a whole lot better. When can this guy come home? When can this guy come back to the harbor? Well, obviously, when the depth's starting to increase, right? Right at this point. So he's got to leave by here. He can come back at this point here. Okay, let's find out what that value is. You betcha. Second calc, find the intersect. Okay, mouse it over. There he is, right there. Enter, enter, enter. He can come back at 7.87. What is 7.87? Let's figure it out. Second quit. Okay, let's go x equals 2. There's my 7.87. So that means at 7 hours, so that's going to be at 7 o'clock in the morning, right? Plus this 0.8739 stuff. Well, what is that? That's 0.8739 of an hour again. So let's get rid of the hour because we know it's 7 hours, okay? But I want to figure out what is 0.87. Well, again, multiply by 60 minutes in an hour. And you find out that, oh, look at this. He can come back at 7:52 in the morning. And he can come back into the harbor and finish his business. Isn't that a wild question? I just love questions like this because it makes so much more sense that we start doing sinusoidal functions with some sort of practical application.